This is FieldAid, an offline disaster response copilot built for the Gemma 4 Good Hackathon. This branch contains a walkthrough demo that can be played by anyone watching this video. Link to the Colab notebook is in the description. The core idea is simple. When floods, fires, earthquakes, or storms knock out internet access, responders still need intelligence. FieldAid runs locally with Gemma 4 through Olama, stores incidents in SQLite, uses bundled emergency guidance for citations, and creates handoff packets that can be synced later. The walkthrough folder contains a self contained guided demo. It includes the Colab notebook, the web app changes, and the walkthrough controller. The local media files for flood, fire, hurricane, and earthquake scenarios are also here. For video purposes, I already ran the Colab setup. The notebook clones this branch, installs dependencies, starts Olama, checks that the Gemma 4 E4B model is available, copies all the walkthrough files into the app, and starts the fast API server. The first model pull can take a while because the Gemma E4B is about 9.6 gigabytes. That is expected. After the model is present in the runtime or locally, the notebook skips the pull and starts much faster. The important point is that after setup, the app runs locally. The models present run through Olama. The database is local, the media stays local, and the emergency guidance is bundled with the project. This is the FieldAid web app. It is designed for the first chaotic hours of a disaster response, when teams may only have partial field notes, phone photos, short video clips, and radio updates. This app turns those fragments into incident packets, a summary, action plan, supply requests, SMS or radio update, citations, verifications, flags, and exportable handoff records. Gemma 4 is the reasoning engine. The rest of the system supports it with local retrieval, local storage, a lightweight visual classifier, and an optional YOLO detection for video frames. We have also tuned a Gemma 4 model for FieldAid specifically to recognize disasters better. Instead of manually clicking through every page, I built an automated walkthrough. It fills the forms, attaches the local images or videos, calls the same backend APIs a responder could use, and shows the results in the normal UI. Let's start the walkthrough. Click Next. The first step is the shelter intake. FieldAid fills a field report for a local school shelter with 43 people, elderly residents, insulin patients, limited water, and a blocked bridge. Gemma 4 receives the responder notes, the location, and the role, the requested SMS language, and local guidance snippets. It returns a structured incident packet instead of free text. Here we get the summary, the urgency, extracted facts, prioritized action plan, supply requests, SMS or radio updates, citations, and verification flags. This is meant to help a district operations team move from a messy field note to an auditable response packet. Here you can download the packet, click Done, and it starts the next one. The second step switches to damage assessment. The walkthrough fills a road and a bridge damage report and attaches a local flood image. This demonstrates baseline multimodal response planning. Gemma 4 reasons from the field note and image, while the app keeps. Notice that FieldAid does not declare the route safe. It turns the evidence into operational priorities, closure, alternate route planning, inspection, communication. Now the walkthrough uploads a wildfire video. FieldAid samples frames locally, sends representative frames to Gemma 4, runs local classifier support where available, and creates an incident from the video evidence. The output includes the likely disaster type, model summary, sample frames, local classifier aggregation, supporting detections, and a created incident record. The next video tests a different disaster pattern. This is a hurricane impact clip. The same local pipeline is reused, sample frames, analyze the event, aggregate evidence, and create a response record. The goal is not only classification, the goal is converting video into operational awareness when cloud tools are unavailable. Here it shows the likely damaged and the accuracy score with some observations and the annotated frames. Here it has marked the people, an umbrella, and the dilapidated structure. This step is a safety and trust gate. The question is whether an area near the fire is safe for civilian access. FieldAid should not make unsupported safety declarations. It should identify visible evidence, cite guidance, recommend caution, and route the decision back to the human responders. The important behavior is restraint. The system provides evidence and recommends actions, but it does not replace incident command, firefighters, medical staff, or structural inspectors. It recognizes correctly and it sends a Discord draft. Second trust gate asks whether civilians can safely cross a flooded highway. This is exactly the kind of question where an AI system should be careful. FieldAid is designed to refuse unsupported safety claims and instead recommend inspection, closure, alternate routes, and human verification. What this shows is no unsafe route claims, flood specific caution, human verification workflow. Roadway is completely blocked by extreme congestion, do not attempt to cross. Flood with 56% accuracy. This step uploads an earthquake impact video. This demonstrates that the same workflow can handle multiple disaster categories without changing tools. Again, the important output is not just the label, it is the incident packet, visual evidence, priority summary, and downstream handoff record. What this shows is multi-disaster coverage, video to incident workflow, local operation with bundled media. It has a confidence level of 95% because of the visual evidence. And the accuracy is 64%. It has recognized a person and the umbrella along with the debris. Now the walkthrough opens the operations dashboard. The dashboard aggregates the incidents created during the previous intake and video steps. This is where a response lead can see urgent medical needs, water shortages, blocked routes, and verification flags across the local incident log. The incident log becomes visible once you refresh the page. The incident log stores every generated record locally. Each incident can be reviewed, status updated, and exported as a handoff packet. This matters because disaster response need auditability. FieldAid is not just answering questions, it is creating records responders can review and transfer. This step demonstrates handoff and sync preparation. The FieldAid can create message drafts and export records, but it does not automatically send them. This is intentional. The system supports responders while keeping final dispatch decisions under human control. The final step shows offline sync support. When the network is unavailable, incidents can stay local. When connectivity returns, responders can export the queue and move it to another system manually. This closes the offline first loop. Local reasoning, local records, local handoff, and sync later. FieldAid is not just a replacement for responders. It is a local disaster response Copilot for the first hours when information is fragmented and the network is down. Gemma 4 provides the reasoning layer. The application adds local retrieval, structured incident records, visual evidence, safety flags, and handoff workflows. When the network goes down, intelligence should still show up.